Start streaming. Good. Okay, so welcome back. Still more than half of you. Okay, so last time we had the general stuff and signals, and then a couple of notes about the exercise one, which deadline was just about 2 minutes ago. Okay, for myself, the deadline is just so that when I start looking for those answers, the returns, I would like to do all of them at once. So fundamentally, I try to have you doing the exercises before the next topic starts. But most probably I will start looking at the exercises on the Tuesday morning. So you have some, some time there to play or whatever you do. But anyways, and then on the other hand, this far I haven't put any real big penalties on being late. But don't count on it. Okay. Oh boy. And another one, when you're doing the exercises, I'm actually asking you to use your own Google account, not own, the company Google account. So Metropolia.fi actually provides you the Google account. Use that one. Why? Just because I want to know whoever is returning those exercises. I need to know who that was, since otherwise if you are using your Google own personal private Google email, it maybe have ASX12568 or something like that as a name, then you forget your name or write there something that I don't recognize from the list. So that is just basically for my convenience, that I can find whoever returned that the report. Okay. Then I also yesterday got some requests of sharing the original template. The idea is that you make your own copy, working copy, and then you can edit it. I'm not giving anyone permission to edit the original template. Just taking a copy to your own Google account and then start filling it. Okay, with those notes. So last time we had the general stuff and the signals, signal fundamentals, like sampling and some fun stuff, and general the generic signals, how to generate voices and noises. Today we go through some of these systems fundamentals. Okay, as usual, I have the my favorite photograph there. I really would like rather be fishing, but yeah, the work is actually it's disturbing my fishing season. But anyways, I have to work so they can get fishing. Anyways, so the I will replace this face by the today's material when done. But anyways, so let's go to the DSP fundamentals, and there we go. So digital system fundamentals. So what happens to a signal when you go through a system? So basics is on this one. So those are the 4 fundamental digital signal processing operations. Everything else actually can be done with these. So these are the basics, and then when you need an operation, you basically have to work with these. So add, okay, that missing character is actually minus. Okay, So add is either plus, add, or minus. Minus means a subtractor, but it's fundamentally the same operation. So plus. Well, actually, that might be a sum which is missing there. Yeah, I think it's a sum. So it's either plus or sum symbol. And the math simply plus, and block diagram symbol is a circle with a plus or sigma inside of it. Yeah, sigma is missing. Sorry about that. Then the other one is scaling, meaning scaling by scalar, meaning now I should actually start writing on the whiteboard, and hopefully this one more or less shows the whiteboard. I brought here some whiteboard markers. I hope that they are here. Okay, so basically the scaling is such that you have an input x of n, and then you basically have a scaling with a constant, meaning mathematically it's just that you will multiply the input with this scalar, meaning a constant number. There you go, that's a basic operation. Another, the previous block diagram symbol for the add, for example, well, I think I will make an example of that one. So then we have a delay. Delay is a fundamental operation, meaning that you take this signal, for example, here, put it on the delay. It's either D or Z, or if you have a multiple delay, then you make a D square or Z to minus something. Okay, single delays basically just D. Okay, let's put some arrows there. And here we have x n minus 1. One time step delay. Or actually, if we had multiple delay, for example like this, z to minus 2 would mean the same as delay this point by 2 time steps. So in here we have x n minus 1 minus 2, so minus 3 actually. Okay, so you can nest these things, and of course then you can start building the system using these fundamental blocks, making some other, say if this was A0, here we have for example A1, and just for a good reason I will mark this one A3. Why I started with the A? B is so much better for this one. I will tell you later why. B0, B1, B3. Okay. H could be also used. But anyways, so here we have B1 times x n minus 1 plus B3 x n minus 3. Okay. Just an example. If we had a block called sum, like that one, that's actually the convolution block right there, filter block. Okay, direct form. So basically this block diagram symbols are used to construct or define or show what the system actually looks like, and that's actually the implementation of the system when we do it on block diagram level. This will actually come later also. This formula is called the difference equation, and this is the block diagram or flow chart, or well, it has plenty of different names. Block diagram or flow chart, and that actually is the implementation of the system. Design. Okay, this is just the formula to calculate the output. Okay, simple. About the basic properties of the system. Okay, let's see if I can actually, before going there, haha, wow, it almost shows up there. Good. So that's the block diagram flow chart and the what they are called. Okay, good. So let's go back to the this one here. So properties, fundamental properties of any digital system. 4 different ones that you should actually somehow recognize when you see a digital system, or determine or measure if nothing else works. So first one is very important for any, say, audio processing or video processing system. Well, mostly audio. Linearity. It would be nice actually if we have so well-defined system that we can kind of forecast whatever, when we know the input, what comes out. So that's actually what it's in plain English. So basically it's also that we can apply superposition principle. And mathematically, the weighted sum of inputs is the same as weighted sum of outputs. Okay. I need to use the whiteboard again. Unfortunately, I think it'll be a little bit well, maybe it will show up, maybe it doesn't. I try to be clear. Okay, so linearity. So basically, we can test the linearity quite simply if we're taking a look at the formula there. Oh, well, yeah, sure, taking a look at the formula. Now we can take a look at the formula better. So linearity test actually goes so that mathematically we have this function. So that is the function what a system does, and a scaled input x plus scaled input y, 2 different inputs. So this is input, this is also input. Okay, and this should actually come as scaled output plus the scaled output of the other inputs. Okay. And this is something you can test. If you get equal, then it's linear. If you get unequal, then it's not linear. Very simple. And basically what it means that if we have a system, that's the system F, and basically have two different okay, let's see. So this would be the same as making a signal. Okay, this one here. We have X and input, Y and another input. I started a little bit funny place. Okay, well, let's see what happens. I have the scalar sorry, not one, but A and B, and then we have a sum. Put it inside of that one. Whatever comes out is this one here. Then we basically test if this one is the same as running signal X and Y to the same system, and then actually multiply this one with A, this one with B, and sum the output. Okay, they should become the same. So it's just a matter of how to how you feed this signal in. Are you feeding it as the summed signal or not? One very good example of a system which is not linear is when you saturate an amplifier or saturate anything. This is basically if this signal here already saturates, then that signal is just saturated multiplied by a factor A, and then you sum this signal to that one. Okay, I'll just make this example. So if you saturate this part, you still get the signal Y on the other side. Okay, so this one saturates. This is this signal, but on here, if this one saturates, then definitely it saturates also with the sum. So which means that you have only saturated output. You cannot sum it if you saturate in that part. And these are different. The different. So saturated systems are never linear. Okay. So that for that reason we cannot let these systems to saturate. In a digital world, that will be same as the overload. Okay. So that's the linearity. And before I lose that one, I'll take a picture. Okay, and we will actually test the linearity on MATLAB exercise. Basically, we are doing exactly this kind of test. And by the way, here the linearity test should be actually tested with any value A and any value B and any signal. We just need to do, say, random enough of tests to see if that is valid for any signal. All right. Then the next part is about causality. Okay, I need to check the so causality of the signal of the system. So basically there is no effect before action. That's the causal. Okay, so no one falls asleep until I start talking. Not before. Okay, but that's actually a good example. People are never causal. Say the stereotype of engineer is very causal. Does only what is told to. That is one of the jokes, right? Okay, what engineers do. Say whatever the boss tells them to do. Okay, that would be causal. But actually, the real engineers always also give some hints to the boss that he thinks that the boss is giving the orders. But on the other hand, that the way of doing it is the engineers can do whatever they please. Okay, that's another joke. You don't need to laugh that much. Okay, so causality. There is no effect before action. So causal is a good property, for example, for parking meter. If you put a coin on parking meter, you expect that one to give you some time. If it's not giving some parking time, then it's behaving non-causal, and that's not good for that device. Okay. On the other hand, this is not about good or bad. It's same as the linearity. Basically, the clipping of the sound is a good thing if it's basically the volume would be above 80 dB in average. Okay, you don't want your ears to pop when you have a loud moment on the music. That's for your protection. This sound is clipped. Okay. Causality, the same thing. No, this is not yin and yang. This is not evil and bad. Oh, this is actually yin and yang. Right, yes. But not about good and evil. So, causality, simply put. So there must be an action before reaction. All physical, say, things without any intelligence are causal. Rock doesn't fall unless you drop it. Okay. Causality. Take note on how to write this one. This is not casual, but causal. And this actually means that if we have a signal, test signal, non-zero test signal going through a system F, and you get some sort of delay, let's mark it just y of n. Basically, then you should have a the same effect with the same amount of time delay also with the delayed signal. So the system behavior does not change in between of those signals. And that's exactly also the test. And that's the function output with that input. Say usually the causality is something that is especially when you're talking about the digital signal processing systems. The real-time digital signal processing systems are usually the causal, but not always. With digital signal processing on post-processing, you can do non-causal things that would actually be quite, say, hard to do in the real life, but or real time, but on post-processing you can also, for example, reverse the time of the data. There are some nice things you can do with the reversal of time, like a filtering without any delay. Okay, good. Next would be stability. Woo, I have that one there. Wow. So next up would be about stability of the system, and now we are talking about bounded input, bounded output stability. Let me take a picture of that. Stability. Okay, stable system. What it actually means that if you have the system here and our input have some boundaries, so this is bounded input. Like that, and basically you should also, for all of these bounded input you should also get bounded output. It could be something else, but still some upper and lower bound. Okay. Good property. For example, amplifiers are usually bounded input, bounded output stable systems. On the other hand, you can also get nasty systems which are basically starting at some point to saturate. On digital work, this usually means bad things. On digital world, you try to keep all the systems as stable as possible. Okay, but not stabler than that. Okay, so the stability, it's about the for any input which is within some bounds. I think this was bx and this is minus bx here. You can find the some values, also some bounds for the output too. Okay. The fourth one. Shoot, causality. I think I put the time shift invariance instead of causality there. Sorry, yeah. It's about the same thing, but not quite. Sorry about that, my mistake. That was the second mistake in my life. So this is the time shift invariance. Okay, sorry, my mistake. The causality So here you basically, on time shift invariance, you have the system which does not change. Causality is simply, it's a little bit, it's not that tight constraint, it's just that the system output is 0 before you have a signal coming in, whatever the signal is. So the signal starts at at 0, then this signal cannot start before 0, so it can start after or at 0. So output starts at 0 or later, sorry. Okay, causality. So time shift invariance was about the parking meter. Causality is like yeah, there was that boxer against professional, what is that, the other fighter? Yeah, that game. So that professional, the fighter actually was more about the causal, just when it get a bounce reacted on that one. But the professional fighter was non-causal, since he was actually kind of one step before the other one was hitting, so he was cautious about it. Okay. Yeah, that works. All right, so 4 properties in total. Okay. So linearity, causality, stability, time shift invariance. And on MATLAB session, we actually go through 3 of them. Actually, I think we go through all of those, but you will have exercise only on 3 of them. Yeah. It seems that these computer fonts don't match. That box should be sigma. So the systems are described mathematically using difference equation. So that is only the mathematical expression of how the system behaves. It can be also used to calculate all kind of stuff, but don't take it as an implementation, since it's not implementation. All right. Equation. Then I think next part would be the flow chart or block diagram. So difference equation is simply the formula for output, and the block diagram is the implementation. And in generic forms, the LTI system, meaning linear time shift invariant system, doesn't the stability comes later, but anyways, linear time shift invariant system It doesn't need to be causal, but still LTI system. All the LTI systems can be described like this one. It's a capital sigma of A index k times the output with the time delay of k equals same as sigma bk times x n minus k. Okay, and basically this would be infinite sum from on both sides, but if the system is then causal, as the most of the systems are in real world, we can start this one from 0, run it to some index, maximum index number, same here. Okay, that would also add some causality to the system. All right, so basically this must start at 0. This can start later. All right, so that's a difference equation in say generic form. Okay, comparing the pictures I wrote there, I changed the A scaling factor to B just because that's the common convention how to describe those parameters. So for input you use B, and for output you use A for historic reasons. And that's where you will make some mistakes. Last time about 25% made the mistake between A and B, which make a big difference on the implementation side. But anyway, so generally this is formula for output y of n. We can take, if we set the A0 is 1, well, we can do it even if it was originally 1. We can basically divide both of those sides with the same number, so we can fix one parameter to be 1. Okay, so if A0 is 1, then we have the formula for the calculation of current output value. I need some room. Current output value simply, okay, this starts from 0, B0 times x of n plus B1 times x of n minus 1 plus so on until we get into Bm times x of n minus m. That's the last delay term. Then this part, the rest of it actually it's a feedback of this output, and that actually, well, I will just put plus here, but it continues of course as minus. That's another mistake that you can make when you are having a difference equation on this form and starting to think of some other things like the transfer function. But anyways, the sign error is something to look at. So, but that's A1 y n minus 1. Okay, that's the previous output value. A1 A2 y n minus 2 minus da da da, and the last one is A n times y n minus n. These values don't necessarily be the same. It's just a matter of where you have the rest of those as zeros. All right, so that's the formula to calculate a output for that system, which has the feedback. Hi. Okay, that's the feedback. Negative feedback, so to speak. Doesn't really matter here, but anyways. Okay, the corresponding block diagram. Okay, this is implementation, and there is always more than just one implementation. So, but this is so-called direct form. One implementation of block diagram would be just to take this formula and start doing the, for example, like this. So we have input, and we are trying to get the output IFN. Okay, and then we also need these time shifts. So we have a shift register here, and we have delay or Z2 -1. It doesn't matter. I usually use the Z2 -1. More delays, Z2 -1 again, and so on. Z2 -1, so that here we have xn minus m. Okay, and we get the taps on each of these to get the other delays. And then we have the BK here. So we have B0, yes, B1, B2, and this one is multiplied by BM. Okay, then we can start summing. So these are summed together, and one way to do the summing is just to make big block here, but the computer doesn't work that way. It only does subsequent sums, maybe in several cores, but each sum is just one instruction between two numbers. Okay, so we can start, for example, from here, do the summing kind of, well, that goes some summing block, but anyways, the previous comes here. So that's the, say, general way of showing up, okay, this is the sum of all of that stuff. All right, this is not done. This is just half done. So we have just those parts. Now we need to do the feedback part. And there we need a feedback with the time delay. So let's do the same delay kind of thing. Here Z2 -1. Again Z2 -1. To the last delay. All right, and let's take taps. Ha. For example, that one. Oh, yeah, or AK. A1, A2, AN. Those are the scaling factors, and again we need similar kind of summing chain here. In principle, we can draw it so that they will actually, this will be sum of three values, but for computer, again, it doesn't make any sense. So if this is an implementation, then you would actually have a separate summing junctions here. And that's your system. That's the implementation of the system. All right. I will go a little bit forward since this is so-called direct form 1. Just to make you think of the importance of linearity and what it actually means. Basically, we have some memory related things here. Each of these delays actually mean one memory location. You need to put previous values into memory. Of course, on the computer we have enough of memory, it doesn't matter. But on embedded systems you never have enough of memory. At least you never have enough of RAM memory. So fast memory that you can do the calculations. Okay. So this will do fine for media engineering with Java. Oh no, with Java you cannot do any of this. Oh no, bummer. So, actually let's take a closer look at what can be done. Just checking the okay, view is okay. Good. Nice thing about this linear, I told about the linear time invariant systems, yes, LTI. Linearity is actually, you can think of these as two separate systems. Which, well, they are separate. This is the sum of inputs. Then that sum is turned into this system, which is basically sum of that input with feedback. Okay, I call this one F1 and this is F2. And since these are linear, you can also reverse the order. So superposition, A plus 1 is same as B plus A. So we have, instead of that, we would have we have the first system first here. Okay, x of n actually comes into the system. Actually, it comes to the plus. Okay, there's the summing chain here. And we have the same, this will be a big mess. Same values there, it's A1, A2, AN or M, yes. Then we have the delays in between. Okay, here we have the delays, C2 minus 1 from that point. And in between here, Z2 minus 1 again. Here we have a lot of these taps. Okay. How about the other side? The other part, F1, had this on the beginning. And then these multipliers. Sum something funny here. Those are has exactly the same contents in each of these. So basically we can get rid of either one of them by just tapping so those away and tap from here. Well, that goes somewhere in there. Okay. So this one saves half of the memory. And if this was a either very fast signal processing with limited amount of this fast memory, this would make a big difference. Speed up factor something like 1.8 practically. Okay, good. So the implementation actually does make difference what kind of implementation you choose. Back to business. Okay, so difference equation. There's just an example. So just a numeric example. 4-point running average filter. Okay, and two different ways of doing it. So 4-point actually, you either calculate 4 subsequent samples and just calculate this average of it. That's fine. You would do a multiplication, well, once, and then the 3 times addition. Or you can do it also a little bit smarter way, or using feedback. You multiply it once, yes, but you use the previous value at 1/4 of the input and take out the old 1/4 of the input. So that's fundamentally 2 multiplications and 2 additions. Oh, no, sorry, 1 multiplication. Yeah, 1 multiplication. Since there's some same multiplying factor, you don't need to multiply each one of those separately. You do first the sum and then multiplication. Okay, so there are plenty of different ways of actually do those. Maybe I should also draw those there since I have some space, or did I have the oh, okay, well, I have the yeah, I have that one actually here. So you can take off the 1 out of 4 multiplier, multiply either the input or the output, I don't care. Multiplying the input, actually, if you have real data with limited resolution, you would cause you some trouble on that point. On the other hand, that sum could also saturate the system on the fixed point precision. So, but anyways, it's some of the things that you need to consider when you are going into a real implementation on the system. But anyways, it can be done that way. Or then with the feedback, yeah, that'll work. Another question is how many memory locations you need. You can even go one step further with that one. Or it's basically either you need more memory, or you basically okay, what is the catch here? No catch. Okay, but anyways, those are at least the 3 different implementations on how you can make this very simple 4-point running average filter in so
In the last case, there is that minus x to n minus 4.
yep.
Which is 4 times delay. Is it that it doesn't just accumulate indefinitely and just
Yep, yep.
and
Yeah. So yes, so it's a minus on that. Okay.
So then
Yeah.
time you at the next value.
Yeah.
And
So
then
basically
one
the
line you
yeah.
take one
Yes. So
already
yeah, and this operation is always plus. So if you need to do the minus, you need to do it like this: minus and plus,
Yeah.
differential. Right. Okay. Maybe I should actually draw a little bit of just for fun. So we have the x, some values here, like that. The first one would be average of these. Right, y of n comes from these. 0.4 times sum of these. 1.4, 1 divided by 4 times sum of these. The next one would be calculated from this. So basically you already have that sum. You just need to take that part out of the sum and add this one. Okay, got it? Yeah, something like that. Simple. For 4-point average, it doesn't give you much of the advantage, but for example, 100 points average, it's quite a lot of difference. Okay, good. Scribbles. You take more pictures. So next is the fun part, which is the transfer function. How many of you attended on Friday the Timo's special lecture on the mathematics? Excellent. Now you know everything about this. Not quite. Okay, now we are jumping into from time space into frequency space. So fundamentally, if we want to look at spectral properties of system, we have to actually go into the transfer function. And this time you can take a transfer function just simply as the z transform of discrete time system. Yeah, okay. Anyways, it's quite mechanical way of how to do the transfer function. Later on you will find out better what it is. So it's still the same system, but it helps designing the system or analyzing the system spectral properties, like how the frequency response would look like, how a signal of some say sinusoid signal passes the system, how transients pass the system. But anyways, transfer function. Did I remember to? Camera is turned okay, but did I actually remember to put this one on camera? No. All right. So transfer function. It's basically z transform of, not quite, but anyways, difference equation. And basically it's the definition of transfer function is, I have to take a look at it myself, okay, is the z transform of output divided by z transform of input, okay, in this order. So basically, if you are doing any calculations on frequency space, then you can always do the calculate what is the z transform of output by multiplying the z z transform of input with transfer function. Okay. For example, if you knew that, okay, I need the impulse response of a system, you can put the z transform of impulse here, yeah, and then multiply it with this one. And they are actually quite nice tables which you don't need to use. But they used to be really nice tables for the most commonly used z transforms of some functions. And by this tool you can actually do it in closed analytical way, meaning pen and paper, what the system output would look like without any computer, just pen and paper and those tables. Okay. On the other hand, this also is say basis for any filtering, since the transfer function, if you evaluate transfer function at unit circle, that's same as the frequency response. All right. Finally, something used for the transfer function. Okay. And also some things like stability. Stability of the system. So does it work or not? In digital world, unstable systems do not work. Or at least they don't work as you wish. So basically, analyzing the transfer function will tell you if the system is stable or not. Okay, so actually if you take a z transform of both sides and then take a couple of properties, let's see if I have the properties there. No, I don't. Okay, a couple of properties. Your transfer function actually comes simply like this. bk times z to minus k. Okay, that's the complex value. Don't worry about it now. If you set the complex value to that one, it would be the frequency response. But that's what it looks like for this difference equation. Well, maybe not like that. Let's see. K from 0 to n. No, that was m. K from 0 to n. Yes, that way. Okay. So that's the transfer function. Now I don't know if your previous studies actually have anything about how to analyze system behavior in continuous time space, meaning analog electronics. Did you have anything? Oh, you have missed a lot. Yeah, I'm feeling myself so old now. But anyways, I'm one of the last of the dinosaurs here, so just to let you know. Okay, so Z transform the difference equation, and it comes like that, and that tells you everything about the system's frequency responses and or frequency world, so to speak. So it's the representation of the exactly the same system in frequency world. Okay, of frequency space. Good. All right. Did I take a picture of that? No, not yet. All righty. Now when we are in the frequency space, let's go a little bit forward and look at the convolution and also the correlation. Okay, so convolution was last week. I told you, okay, we just convolute the signal with the system response, impulse response, you will get the filtered signal. And then we had this excellent example of measuring the system response by snapping, meaning putting an impulse. And if a system is linear, if you think that the system is linear, then basically the superposition, and any signal can be described as a superposition of delayed delta signals, snapping sounds with the different weights. Okay, so basically we can regenerate that space for any signal by convoluting the snap or impulse response of the space with a signal. Okay, so if you want to hear what Madonna would sound like in Sagrada Familia, you go to Sagrada Familia alone and snap your finger. Okay, maybe not. Being alone in Sagrada Familia would be probably a felony. You have a question? Yes.
Is it fraction correct over there? Is it B and M belongs to Y? Because what you are cleaning right now.
Yes. Exactly. Let's do the math. That was wonderful that you asked, since this probably will save the rest of you if you listen. The trouble. Okay. This is defined as z of y of n divided by z of x of n. Let's go back to this one. I need to get this one on tape. This will save a lot of energy. All right, tabula rasa. Excellent. So this was b k y no x n minus k. Let's do the z transform of both of these. So z transform, not Laplace, but z transform this equal to z transform of that. Since the z transform is a linear operator, you can do that. Okay. You have z sum a k y n minus k. I start disassembling it. Linearity means that you can take the scalar out and also the sums separate. So this is exactly the same as z. No, sum of a times z. Okay, y n minus k. Then there's trick. I have it somewhere on the slides, not here. Time shift of z is actually the same as well. It's it was on the block diagram. Z2 minus 1. Time shift equals to Z2 minus that one. So that one is actually as sum of AK z2 minus k times z y n. And this would actually come up as bk times z2 minus k times z of x of n. Okay, now calculate this divided by that. Okay. Well, this is just a constant. It's the same in every single one of those that comes out. We will have, well, let me go a little bit further with this one. Y of n times that sum ak z2 minus k equals to z xn times sum of bk z2 minus k. Okay, now divide by this and that. We have z2 yn divided by z2 x of n, which is the h of z, equals to, okay, this will remain at the top of the equation. Numerator, oops, z2 minus k and divided by a k z2 minus k. Yes! It works! Any questions? All right, so yes, and as you can see, it's very easy to make the upper and lower polynomial coefficients, and that would be catastrophic if this was a filter. Okay, but anyways, I proved the point. Good. Oh boy, I'm good. Oh, okay. And even I have some important z-transform properties there on the table. So it's linear. So we use the linearity to break up these the sums, and then use the time shift property to take actually the time shift out of these. Okay, we didn't use the unit impulse and unit step properties, which means we didn't need to. But basically, for that unit impulse or unit step, now how to calculate the unit impulse response in frequency space. Okay, you just have the instead of x you have the delta, so okay, you can do the math. That will be pen and paper approach. Yes, so basically this is already the impulse response, the transfer or z transform of unit impulse. Okay. No, sorry. Response of the system with unit impulse. I'm drawing there funny things. Response okay, there we go. Better. So there's not too many things actually you must remember here. So the difference equation, it has the system parameter. So this difference equation is how you formulate the equation for the system mathematically, time-based system. It has the delays and these parameters. Then you have the block diagram or flowchart. That's basically your physical implementation. In which order you need to do the calculations to make the system work. Okay, transfer function. That's basically, it has exactly the same parameters as in the difference equation. So you know them. And then you can actually start analyzing the system on the frequency space. Or this same thing also, it's totally the same the other way around. You design a system in frequency space, meaning you do filter design. Select the parameters on the frequency space for the transfer function, and then those are exactly the same parameters also for the difference equation and or your system implementation. Okay. Let's see. Yeah, that also sigma is missing. Sorry about that. So I need to figure out how to fix it so that it will stay the same on the different platforms. And then there's an example of transfer function of this 4-point running average filter, which is excellent, since now we can basically take a look on the transfer function. So we have the difference equation y of n equals x of, well, 1/4 times x of n plus x n minus 1 plus x n minus 2 plus x n minus 3. Okay, there we go. And then we just need to determine what are these values here. bk. 1/4 is the first one. Okay, so b0, b1, b2, b3 are the same ones, which is 1/4. Then what are the these a values? AK. Where is the a0? It's here. That's the a0. 1. At least that much you have every single time. Where are the rest of them? It doesn't really matter, since we can just draw this transfer function there, which is h of z equals numerator 1/4 times z to 0 plus 1/4 times z to minus 1 plus 1/4 times z to minus 2 plus 1/4 times z to minus 3 divided by 1. Okay. Which is same as 1/4 1 plus c to minus 1 plus c to minus 2 plus c to minus 3, which is exactly the same as 1/4 times 1 minus c to minus 4 plus let's see, 1 over something. No, not like that. Sorry. Equals to 1/4 times 1 minus c to minus 4 divided by 1 minus c to minus 1. Yes! How come? Well, the feedback. Remember the feedback system. 1/4. So that corresponds actually to the yn equals to 1/4 times x of n minus x of n minus 4 plus yn minus 1. Okay. And, well, if you remember something about the polynomials, actually when you calculate the well, if you do that division here, you will find actually that there is one. So that one cancels out, and that will be the one which is remaining. That used to be one of the standard kind of questions on Timo's course on polynomials. Not necessarily on the z-plane, but it's the same. It's exactly the same. Okay. Wow. And I actually did it the same way as on my slides. Excellent. Okay, sorry about the missing sigmas again. I really have to do something for the sigmas. So, zeros and poles. Zeros and poles are the special points of this polynomial. Zeros and poles. Zeros are the same as the numerator polynomial zeros, and this is actually the denominator polynomial, the roots. Okay, roots of numerator. Oops. Roots of denominator. Okay, on that polynomial, which can be also written the following way. So how many roots actually nth order polynomial has? Okay. Well, let's multiply the both of these on z to power of, well, that's the maximum of n or m. Let me just call it mn. Okay, so bigger one. So if we multiply the bigger one up there, okay, going from 0 to m bk times z to mn minus k, okay, and that is now a both are positive polynomials now. Now we can actually calculate how many roots they have, and they have exactly the same amount of roots as the highest order polynomial actually tells you. So basically, at the beginning we would have b0 over a0, which is the overall gain of the system, and then we can actually show this same equation as the following. We have the 0 points of numerator, which are the roots of the numerator. So we have the zeros of the system, zk, and we have the okay, I need some, yes, that's actually the scaling factor, maybe z minus pk. Okay, it's just a simple calculus. I'll show you on the MATLAB how this is done. But anyways, now we have these are the zeros, these are the poles of the system, and we can now make a graphical representation of this. Graphically, we will draw a unit circle on complex plane, real part, imaginary part. We can make this one Argand's diagram by just putting here the gain, overall gain of the system. And then we will mark these zeros. Let's see, 0 with blue color. For example, like this. Z1, Z2, Z3. Okay. And the poles. Poles, for example, like this. Here. Pole 1, pole 2, pole 3. This is very simple trick when you have MATLAB. Since here we have the polynomial coefficients, which actually are, well, the same as the system coefficients. So, yeah, polynomial coefficients. And when you put this vector into MATLAB and ask roots, it will give you the zeros. Okay, roots of bk polynomial is the same as zk. Or the other way around, you will get the coefficients back by saying the polynomial coefficients of whatever the roots are will give you the coefficients. Okay. But anyways, this is a linear time invariant system and it's causal also, but you can take a look at the these values to see if the system is stable or not. If the roots of the denominator, meaning the poles, are inside of the unit circle, then the system is stable. Easy. System is very stable. Actually, and this is if and only if. If they are outside, then it's unstable. If they are on unit circle, then it's critically stable. Is there is a this I stable. Is stable, yes, thank you. So that's one way of checking if the system is stable or not. But then you need the system parameters, of course, system coefficients. Okay, so yeah, zeros and poles. And that comes from the transfer function. Yes, transfer function is very important. And yes, now we are actually looking at the complex plane where this here is actually e to j omega. And omega here is the, it's not physical frequency, it's angular frequency for the digital systems. But anyways, it's directly proportional to the physical frequency. Okay, so and in order to calculate the frequency response, we are evaluating the transfer function on this unit circle. And if the these poles are inside of the unit circle, then the amplitude response actually remains quite nice and smooth, and you know, in in some boundaries. If it gets outside, you will get funny looking frequency responses. If it's exactly on the unit circle, then basically it depends. Let me draw you an example. Since we have this transfer function of 4-point average. By the way, this also shows the so-called order number of the system. Okay, so it's actually the highest polynomial number on this form of transfer equation. It's not necessarily the highest delay. Okay, so this system would be third order system. Polynomial on that one or that one. Okay, which brings us to that question. Since this is a 4-degree system, is this a third order system or fourth order system? There are actually 3 delays, which tells us, okay, it could be third order, or here it's actually 4 delays, so it sounds like it would be the other one. Okay, for example, this here average filter. Okay, there we go. I should draw 2 of them actually. Yes. A bigger ones. A little bit bigger. There. Okay. Unit circle. Then the other one. Unit circle. This here actually have 3 poles, 3 zeros, 1 to minus, actually let's see, 1 plus c, let us see, third to c1, okay, there's also that 3 roots, and they just happen to be, let's see, that's 1/4 of c4 plus c, not 4, 3, 2, 1, 0 divided by z3. Okay, so that's the transfer function in this order, so that I can start calculating the roots. I just have to multiply with z3 to get rid of the negative root values. Okay.
So that's why you get T3.
Yes.
Divider.
Yeah. So I did this one. That one here.
You have to do it on the whole.
Yeah.
Up, down,
Yes.
same time. Yeah.
And that gives off triple pole at 0. So there are always some poles. If you don't have any poles, then you don't have output. Okay, not a good system. It's called OMA. Whatever comes in never comes out. Okay, but the rest of those, one is, of course, it's -1 here. It's just, just testing by, okay, if you put here z2 is equal to -1, the upper part will go to 0. Then the second one is a little bit harder, but not really, since if you put there plus or minus j, that'll give you the same thing. So, well, this is still one of those polynomials you can do the calculus yourself. Oh, right. So those are the zeros and poles. But how about h of z equal to that one there? So I have 1/4 as the multiplier, and then I have z to 4 minus 1, and then I have z to 3 and z to 4 minus z. Right. Right. No, z to minus. Sorry. Like that. Yes. 3. Yes. Okay. So yeah, let's start with that one. This is easier. 1 over 4. Z to 3. Z to minus 1. Like that. Yeah. Do I get the same? Oh, yes, I get the same answer as I should. So that one actually, yeah, actually this one has root z to 4 equals to 1. Right. Z to 4 equals to 1, which happens at 1 or minus 1 or j or minus j. Okay, so this is alrighty, and that has the triple pole here, and then it has, wow, look at that. That's a lucky guess. So basically what happened on this equation here, there's a zero and pole at the same place. Of course, otherwise it wouldn't be the same system. They must cancel each others out, the zeros and poles. It still must be equal to this one. And then we have the canceling zero and pole at the same place. So mathematically, it's still third order system.
Yeah. And you can cancel them
Yeah.
from each other because it's like this is
Yes.
math, but you can
Yes.
cancel it.
Yes, so
there.
you can cancel it here. Doot, doot. And yes, we have this is third order system. So 4-point running average is a third order system. Although on this way you actually use 4 delays. Wow, ugly picture here. And it looks like it might be actually the last one. Let me go and see. Oh yeah, that's unfortunately the this Google Slides, when you do some graphics on it, it's it does really depend on what kind of tube you are making it compared to what tube you are actually showing it. So the imaginary axis should be at the same range as those the 0 points. Luckily, I have still the same poles there. The poles are inside the the plane. But anyways, this diagram here is called Argon's diagram. Did I turn that one? Yes, I did. So that's the Argon's diagram. So it shows the zeros and poles. If the poles are inside of the unit circle, system is stable. System gain. Okay, and there's the nice example of the zeros and poles. All right, stability. If all poles are inside, then it's stable. If even one falls outside, then it's unstable. Okay, if you have poles on the unit circle, then you have critically stable system, which is also called as oscillator, meaning that whatever input you put there, it takes that as the starting point for oscillation. Okay, well, that was a set. Heavy. How many of you have taken your lunch already? Only one? Okay, maybe we have a lunch break. You can take another lunch. So let's continue at 1:15. I hope there's not too much of queues. Okay, thank you.